The dot and cross product of two vectors are easily defined. The dot product, if the vector v is a1i plus a2j, the vector w is b1i plus b2j, then we can use as our definition v dot w equals a1b1 plus a2b2. That is whatever's in front of I for the v vector, whatever's in front of I for the w vector just gets multiplied together, a1, b1, giving us a number that we add to the number a2, b2, which is just the product of the j components. And there's a theorem that we can prove that v dot w is equal to the magnitude of v times the magnitude of w multiplied by the cosine of theta. And really the main theorem is that this is completely equivalent to this. So if this is true, this is true, and if this is so, this is so. Now we can illustrate that. We have the v vector, we have the w vector, and they have some angle between them. The w vector has some length or magnitude, the v vector has a length or magnitude, and the cosine of theta is just a number that's related to how much rotation you've got from the v vector to the w vector. We similarly can define the cross product of two vectors. Now, the dot product of two vectors is just a number. If we multiply these numbers and add them, we just get a number. The cross product, on the other hand, is going to be a vector, and it's going to have the property that's a vector that's in a plane perpendicular to both of the original vectors, so that if the v and w vectors excuse me, are in the plane of the paper, the v cross w vector has to be out of the plane of the paper, perpendicular to the plane of the paper, perhaps in the upward direction or perhaps in the downward direction. Both of those directions are perpendicular to the paper. Now the definition, there are a lot of ways that this could be defined. I'm going to simply say that v cross w is what we get when we evaluate the determinant. And the determinant has three rows, I, j, k vectors in the first row, a1, a2, a3. Now I've skipped into 3 dimensions where we could have a third component to the vector. Up here we're just talking about a1i plus a2j. K is the vector perpendicular to the x and y plane. It's the unit vector in the z direction. And it's not too difficult to imagine that we can have a vector that has an initial point in the plane, a terminal point that's above or below the plane, so that it has I, j, and k components. Okay, so the v vector is going to be assumed to have I, j, and k components, a1, a2, a3, very much like this definition. All we've done is tacked on a third dimension. And the w vector, again, very similar. We just tacked on a b3k, essentially. So now we have this determinant, and if we evaluate this determinant, and just without defining the way you evaluate a determinant, which is something you should know by the time you get to this course, but this determinant is going to be I multiplied by the determinant of the vector if you remove the I column and the I row. And that determinant would be a2, a3, b2, b3. To get that determinant, you just multiply a2 by b3 and subtract a3 times b2. And it looks like I've not written this correctly. That's kind of interesting. Okay. This should be a2b3 minus a3b2, so that would be a2b3 minus a3b2. And for the j component, if we eliminate the j row and column and row, we're going to have the determinant a1b3 minus a3b1. And the j, the determinant we get here, called the 2-1 or the 1-2 minor, is a3b1 minus a1b3, and I did that one correctly. and I also did this one correctly. Don't know what happened to the first one. Okay, so in any case, you should know how to evaluate a determinant and verify that this is what you get when you evaluate the determinant. Now we can say that this cross product has the following properties. First of all, the magnitude of the cross product is what you get if you multiply the magnitude of V by the magnitude of W by the sine of the angle between them. So if we have V and W, we multiply these two magnitudes and then by the sine of the angle theta. Also, V cross W is perpendicular to V, and it's perpendicular to W, so it's perpendicular to both of these, and we have what's called the right-hand rule. In this case, the right-hand rule would tell us that if we put our fingers along V and turn them toward W, our thumb points downward, so that the cross product of these vectors is downward. Now you don't have to absorb all of that, but you have to know that there is a dot product defined like this and a cross product that can be defined like this, and that they have this property, and this property, these properties.